Hey guys, in this recording, I want to talk about I guess, kind of a thought experiment, a problem I created, and that problem kind of relates to a question I saw in class, and I'll just go over the question I saw in class first. So, I think the question was, if I have two identical point charges, right? Let me draw a bad diagram. Okay. So if I had two identical point charges, let's say that that's plus and that's plus, and the distance was, I think it was 30 centimeters, and the angle was, actually wait, no, the rope was 30 centimeters on each side. Oh, what happened there? Centimeters, and the angle was, I think it might have been 30, not sure, but it's fine. What else? I think that was it. So, oh yeah, and the mass, I'm not sure what it was, but let's just say it was 1 kilogram. If this was the setup, what is the charges of those positive charges? So, what is the charge? So this is Q, this is Q. And let's just start off with solving this question first as a warm-up, and then we'll move on to my thought experiment. So to solve this, we will have to first find the distance between, I'll call this charge A and this charge B. So first I have to find the distance AB, and AB is equal to AB is equal to sine 30 times 30 centimeters, which will be 15 centimeters, and I have to times that by 2, which will give me 30 centimeters. Okay, so now that I have my distance between the point charges, I'm going to set that equal to r, because I want to eventually use this equation, q1 times q2 all over 4 pi epsilon 0 times r squared. So because q1 is equal to q2, because they're identical charges, I can rewrite this as a general charge q. So I can rewrite this as q squared over 4 pi epsilon 0 r squared. And just rearranging for q real quick, I'm gonna get 4 pi epsilon 0 f times r squared, all square rooted. And because I know my charge will be positive or negative, it can be plus minus, but in this example it's positive, so I'm just going to take the positive number of the square root. So I have my radius, or my distance between them, and the only thing I need left is my force. And so to get my force, if I just drew the right side of this, B, the force would look something like this, like the free body diagram would look something like this. So this is my force of repulsion, and this is my weight, mg. Come on, there we go, mg. And because the particle, the point charge, is moving tangentially to the pivot, or this peg, or whatever you want to call it. It's moving in a tangent. I want to resolve my forces tangentially. So this angle here was 30 degrees, and if I extended that line, this angle here would also be 30 degrees because of corresponding angles. If I drew in a different color, what that would look like would be, it look like this. (30°) because weight is parallel to this vertical line here. And then from there, because I know that this should be a right angle, this here should also be a right angle since I extended that line, and 90°, or 90° minus 30° will give me 60, so I know that this will be 60. And then likewise, this will be 90. mg is perpendicular to the repulsive force, so I know that this is 90°, and so 90° minus 30° gives me 60° here. And then because I know that this extended line and this rope makes 180°, I know that this angle here gives me 180. So if I drew all of this out, I know that this is a right angle, I know that this is 60°, and this leaves me with this angle here, which will be 30°. Okay, so to draw this diagram again, 30°, mg that's my niece in the back. Okay, I'm gonna have to extend this to make it look like it's 90°. Okay, so if I have t here, and this is mg, and this angle here is 60°, resolving horizontally, I know that these don't look equal, but they are equal. So let me especially label these vectors here. So this vector here and this vector here are equal, and to find this here, I know that mg is my hypotenuse, so I'll use cos 60 times mg, which is this component there, and this component here will be t sine 60. Is that right? T cos, isn't it t cos? Oh, sorry, t cos 30. T cos 30. Yep. And let me just write cos 30 in as sine 60, because of sine theta is equal to cos 180, not 180, sorry, 90 minus theta. Okay, so t, what did I label at t? Sorry, that's supposed to be f. So f is equal to mg over tan 60. Okay. Okay. And my mass is just 1, so this becomes g over tan 60, which is root 3. So g over root 3 is my repulsive force, and so point charge is 4 pi epsilon 0 times my force, which is g over root 3, times r squared. R was 30 centimeters, which is 0.3 meters squared. So let's just see what that is. Square root of 4 pi oh no, 4 pi epsilon 0 times 9.81 divided by the square root of 3 times 0.3 squared. And what my charge ends up being is 7.531 times 10 to the power of negative 6 coulombs. Okay, so that's the problem. And now now here comes my thought experiment, and if I add this, get rid of that. Oh, what happened? That's fine, I'll just color it in white, I guess. Color all of this in white. Okay, now let's go back to the black color. Okay, now the thought experiment was, where's my cursor? Here. How does the particle move? Yeah. How does the particle move? And what I mean by that is, if I drew the diagram again, right, where this is the peg, I actually can't see where my cursor is. Oh, there we go. Okay, actually, let me. So these are the point charges with the mass m. Actually, it's a little too big. Okay. Okay. And let's say they have a positive charge of q, and they're identical, by the way. So same setup, but in this case, their masses are unknown, but both of their masses are the same. So let me just write here, m is m1 is equal to m2 is equal to m, q1 is equal to q2 is equal to q. And how does the particle move? So how does the position of particle, let's say B, how does the position of particle B change with respect to time as a variable? Okay, question mark. And this is a bit of a stretch, but how we're going to deal with this is we can imagine the forces, the sum of the forces, so F net is equal to ma, and what we're going to be using is that acceleration is equal to omega squared r, because acceleration in this system, we can substitute this equation. I think here's what I'm not too sure about, but because this particle is moving tangentially and the radius is constant from a certain point, the center, I think we can use this equation. Correct me if I'm wrong, but I'm gonna be using this equation in my, I guess, thought experiment. Okay, so we'll be using this equation, and we'll also be using F is equal to Q squared all over 4 pi epsilon 0 r squared. Okay, so these are the equations we'll be using, and yeah, we're gonna try and resolve this. And how does the position move, or how does the position of the particle change over time? We're going to be modeling it using theta as our dependent variable. So dependent variable is equal to theta from the normal of this, or from the vertical rather, and independent variable is time. Okay, so let's start this. So let me just make a new slide. Oh, alright, okay. Let me just color all of this in white. Okay. 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 So the same setup, but we'll draw, I guess, stages of how this is gonna look like. So this will be at time is equal to 0. This will be just draw a little bit bigger. Here is theta, and here are my point charges. Time is equal to actually, sorry, no, I don't wanna do that just yet. I think I'd rather say that my angle here is 0. Where is oh, here. Okay, theta is equal to 0. Theta is in between 0 and theta c. I'll just write theta c for now, and then here's my theta c, where my angle is theta c, and theta c is simply the angle at which the system is in equilibrium, or that the net force is equal to 0. The net force on the particle is equal to 0, or in other words, when there's no motion. So just a thought experiment. If the repulsive force is weak enough, theta C will be less than 90 degrees. Okay, we can see that as if we have a repulsive force, eventually gravity will be strong enough such that it will balance at some angle less than 90 degrees. However, if the repulsive force was strong enough, the system should be in equilibrium with the angle, the critical angle at 90 degrees. Was strong enough, the critical angle should be 90 degrees. And we can visualize this, right, with our system going upwards like this because of the repulsive force. And at this point, if the repulsive force was strong enough, it would the weight of the particle would not matter, and so it would go past 90 degrees. However, once it goes past 90 degrees, right, when my angle goes past 90 degrees, they would experience repulsion again, and so they would fall back, I think, eventually to 90 degrees. So that's kind of my thought of how the system is going to evolve over time, depending on the force, the repulsive force. Okay, so this would be outcome 1, and this would be outcome 2. So we'll work on outcome 1 for now, and we'll focus on this here. We'll focus on this here, and we're gonna resolve, and hopefully we'll get a differential equation that we could solve numerically within a interval of time. Okay, so just a note that theta is my independent variable, and theta is my dependent variable and time is my independent variable, so theta will be a function of t. Okay, theta is a function of time. So this implies that theta is equal to theta of t, and so therefore if we differentiate theta, this is equal to theta dot, okay, which is also known as omega. Okay, so we'll be resolving forces now. Enough of the talking. So if we had point charge at some angle, where the angle is between 0 and my critical angle, this will mean that my mg is here, my repulsive force is here. Here the particle is still there, but I'm just not gonna focus on that because the system will be symmetrical about this axis of symmetry. So this will be F, and again we're gonna resolve tangentially to the pivot. So here we go. Okay. Okay, there we go. So this is a right angle and this is a right angle as well. Like we said before, this will be theta. This here will be, because this is 90 degrees and this here is also 90 degrees, here will be 90 minus theta. If I actually draw that diagram bigger, just to help, yeah, I'll draw that whole diagram bigger. So let me just zoom in. So if I treat that as mg, this is the repulsive force. Here will be the tangential component. So, and just keep in mind that the tangential component of each force are equal. Oh wait, actually no, they're not, because it's not in equilibrium. But we know that the motion is going to be repulsive. The force is going to be repulsive, and so it should move upwards like this. So rotating, well, this particle B is going to be rotating counterclockwise. So I know that the tangential force F, the tangential component of F is bigger than mg. So let me just write this here. So that's theta. We know that that's 90 degrees. This here will be 90 degrees minus theta. This here will be again 90 degrees minus theta, and this here will be theta. Okay, and so the tangential component of weight this time will be cos 90 minus theta. So mg cos 90 minus theta, which is also equal to mg sine of theta, is less than or equal to my repulsive component force, which will be F times sorry, wait, let me label that as theta again. F times cos theta. Okay. And so my resultant force F is equal to F cos theta minus mg sine of theta. Okay. And we need to find out what our repulsive force is, and F again is equal to Q squared all over 4 pi epsilon 0 times R squared. Now Q is simply a constant or a parameter, but R squared is also a variable. However, we can describe R to be a function of theta. So remember that. So if this was A here, AB is equal to R. But because we have the length L, the string length is L on both sides, we can deduce that R will be equal to L times sine theta times by 2. Okay, And so this becomes q squared all over 4 pi epsilon 0 times r squared, which will be 4 L squared sine squared theta. And just simplifying this further, this becomes q squared all over 16 pi epsilon 0 L squared sine squared theta. Okay. Okay. Now our net force. Our net force is equal to F times cos theta. So this becomes q squared all over 16 pi epsilon 0 L squared sine theta all over times cot theta, because my cos squared from here will combine with 1 over sine theta from one of sine squared and become cot, minus mg sine theta. Okay. And using capital N, Newton's second law, sum of the forces is equal to ma, and the sum of the forces is equal to m times omega squared times r, which is equal to m theta dot squared times r. But in this case, r is the radius, not the distance between the particles, so we will replace that with L. So this becomes r theta dot squared. And so, zooming out, my what is it? My equation of motion becomes q squared cot theta of t all over 16 pi epsilon 0 L squared sine of theta of t minus mg sine of theta of t is equal to m L theta dot of t squared, meaning theta dot is squared, not all of this. So here is my equation of motion. Just trying to find a highlighter. Maybe a highlighter is here. Yep, here we go. So just to highlight this in a different color. Oh, opacity, turn that down. There we go. So here is my equation of motion, and to solve this differential equation, I'm going to be doing it numerically, and that will be next video, because I need to learn how to use MATLAB in order to graph this and see how the graph goes. So thanks for watching. Hope you learned something. Bye bye.